Question 28 has managed to sneak by most people, although this student did a really good job and got it. This is a question about proportionalities, and this feels like a more A-level difficulty than AS difficulty question, so it's really worth looking at and going over. A tensile force produces an extension delta L and a steel wire of initial length L and diameter D. Same steel is used to make a second wire of initial length 2L and diameter D over 2. So what it's saying there is in our second wire, which is the same wire, same material, but this time it's twice as long and the diameter is half. So it wants to know what's the extension when the same force is applied to the second wire. So force is remaining constant and the material is remaining constant. And that's important because we know if the material is the same, then the Young's modulus in wire 1 is the same as the Young's modulus in wire 2. And what we can see here, this student has identified that this is a Young's modulus question. Young's modulus is stress over strain. And if you substitute in the two individual equations for stress and strain, we get, well, let's just go through it briefly. So if Young's modulus is stress over strain, we can substitute in F over A and delta L over L, but because it's divided by it, we're going to put the L on the top and the delta L on the bottom. Okay, so this is a term for Young's modulus, and in each of the equations, let's come over here, in each of the two wires, Young's modulus is going to be equal. So we also know that F is going to be equal in both. So we can say the force will cancel from both sides, so I'll leave that off. The length, initial length, wire 1, over the area of wire 1, and the extension of wire 1 is going to be equal to the initial length of wire 2, the area over the area of wire 2, over the extension of wire 2. Remember, the F has just disappeared because we can cancel both sides. There are some other things we need to do here, though. We've been asked to consider the diameter rather than the area. So we just need to include that area equals pi r squared, or pi over 4 d squared. So let's substitute that in there instead. Well, actually, the pi over 4 is going to cancel on both sides. So we can absolutely substitute in instead L1 over d squared 1 times by extension 1 equals, it's going to be equal to L2 d2 squared over length 2. So if this is again a little bit messy, now we're asked to consider what's happening to extension number 2. So it might actually be worth rearranging this to give you extension 2 equals, which you should absolutely take a couple of steps over it, but comes out as L2, let's see, delta L1's got to be up here, D1 squared's got to be up here, I think we've got L1 down here, and diameter 2 squared. Okay, so this equation is going to be very useful for allowing me to understand how changes to items over here are going to affect this extension over here. And there are only two changes. The first change is that in the second wire, the initial length is double. So this one is going to be times by 2. Now, if I times something up here on the numerator of this equation by 2, simply enough, it's going to times anything over here by 2 as well. Okay, so that's one effect. The other thing that's going to happen is, remember in the question here, diameter in the second wire is halved. So, coming down here, let's see what that does. D is going to be divided by 2, but of course it's squared. So D is going to be divided by 2 squared, which means it's going to be divided by 4. Right. What happens if we divide the denominator of this side of the equation, by 4? Well, because we're going to make the bottom of the equation considerably smaller, we're going to make this one bigger by the factor of 4. So this is going to have a multiplying factor of 4. Combine these, well, we're going to be timesing this side by 2 and timesing it by 4 for a total change times by 8. So the correct answer here is D.